Okay, this is AQA AS paper 2 from 2016. As per usual, sadly I can't show the paper on screen, otherwise AQA will get my channel deleted as they nearly did in the past. So this is practical skills and multiple choice. First things first, we're being asked to read a vernier scale. I do like vernier scales, they're very clever. So let's look at where the 0 goes past first of all. So on the left hand side we have 1, 2, 3, and our 0 on our other one comes to there. So that's 1, 2, 3. So therefore it's going to be 2 point something millimeters. And which line lines up the best? I'm going to say it's the 7th line. Therefore it's going to be 2.7 millimeters. If you don't know how to read a vernier scale, then have a look at my Young's modulus video. 1.2, we're being asked to find out what the mass is. So an extension of 2.7 millimeters corresponds to a mass of 5.8 kilograms according to the graph. 1.33, we have a micrometer that has a 0 error. So when it's closed, it reads minus 0.07 millimeters. So therefore, it's going from that to 0.44 millimeters. So therefore, the true diameter is going to be 0.51 millimeters. All right, we've been given the original length of the wire, 1.82 meters. We're being asked to find the Young modulus. We know the diameter, 0.51 millimeters. We can find the area from that. Let's do that right now. Area is equal to pi d squared over 4. So that's pi times 5.1 times 10 to the minus 4. If you did 0.51 times 10 to the minus 3, that would be okay as well. And that gives us a cross-sectional area of 2.04 times 10 to the minus 7 meters squared. Has to be in meters squared. And then what else do we know? We know the extension is 2.7 millimeters, so 2.7 times 10 to the minus 3 meters. And we know as well the mass was 5.8 kilograms. Okay, so what's our equation for Young modulus? That's equal to FL over A delta L. We're not going with stress over strain here. We might as well go for the full shebang. But we don't have a force, we have a mass. So therefore the force is going to be equal to the weight. That's mg times L divided by A delta L. So popping that all in, make sure you write down your calculation, because especially with this kind of calculation, because something can go wrong very easily. And that gives us 1.88. Are we going to go to 3 sig figs? Probably. Times 10 to the 11 pascals. 3 sig figs, I mean, I don't know about that. Seeing that we have 2 sig figs for our diameter there, it should probably be 2 sig figs, but mark scheme says either one is acceptable. So we're good. 1.5, we're now using a smaller diameter. So diameter has gone down. If diameter has gone down, that means extension is going to be increased. So what's that going to do to the percentage uncertainty? Well, let's say that the diameter goes down by a half. That means that the extension is going to go up by times 4, because obviously we're dealing with area, and that's proportional to d squared. So let's go back to our equation here. So therefore we can say that this increases percentage uncertainty in area. Because we have larger extensions, we can say it decreases percentage uncertainty in the extension. Now, the mark scheme goes on to say that therefore the percentage uncertainty in the Young modulus is going to decrease. I'm not so sure about that personally. Let's have a think about it. If we've halved the diameter, then that means we've effectively doubled the percentage uncertainty in the diameter. So therefore we've quadrupled the percentage uncertainty in the area, because of course it's proportional to d squared. But that results in 4 times more extension. So if we have 4 times more extension, then that means that we've decreased the percentage uncertainty in the extension by a factor of 4 as well. So they should cancel each other out. So I'm not sure what to make of that answer. I think they're wrong, but hey, if you think I'm wrong, put in a comment down below and tell me why. Okay, so we're being asked to finish a graph that sort of looks like this, and our point should be somewhere like there and there. we need to draw a smooth curve. I don't like calling it a line because I always associate line with straight line, but there we go. Smooth curve of best fit like that. You need to make sure that your plotting is on point, literally. Otherwise you can lose out on easy marks. So that's 2.1 and 2.2. But in 2.3 we've been asked to find the maximum value of epsilon, and so we're looking at the apex of the curve. I'm going to say that that's 1140 microvolts. So long as you're consistent with what you've drawn, you'll get the mark. 2.4, why are we going to get a more accurate result for theta n with figure 6? We're told that this graph gives us the gradient of our previous graph. So therefore, if we're looking at the top here, we can say that max epsilon when g is 0, gradient is 0. We can just read the graph. When g is 0, theta is equal to that theta n. 2.5, we have this equation. G is equal to beta theta plus alpha, where alpha and beta are constants. Determine alpha. Okay, so we know that this is a straight line graph. So a straight line graph is always y equals mx plus c. So that means that g is our y value. Alpha is our y-intercept. We know that x is, sure enough, our theta, and so therefore beta is going to be our gradient. We're looking for alpha. So first things first, let's find out the gradient of this graph. It's not g, but gradients. That's equal to our beta. So let's pick 2 points. I get my gradient to be minus 0.037 using just 2 points. And then all I have to do is plug that into my equation with just any point on the graph. So rearranging this, alpha is equal to g minus beta theta. So I'm going to pick the point. Why not? Let's just do 0. And my theta at 0, my temperature is 280. So therefore, basically just that 0.037 times 280. And that gets me a value of 10.36, let's say 10.4. 2.6, here we have an ammeter. We're being asked to find out what the full scale deflection would be when used as a voltmeter. So V equals IR. So what is the maximum current? Well, it is 100 microamps, so 100 times 10 to the minus 6. Now that's our micro, but actually because we're given our answer in microvolts, we can actually just forget that and just remember that it's microamps, and so therefore it cancels out in the end. Times that by 1000 ohms, and so that gives us 100,000 microvolts, or 1 times 10 to the 5 microvolts. So full scale deflection just means going all the way to the end of the scale. 2.7, scale has 50 divisions. Why is this meter not suitable for the experiment? Well, if we have a look back at our data and our graph, we can see that the largest voltage was around 1500 microvolts. And so therefore, if this is our voltmeter here, and this is our scale, that means that the maximum we're going to get is there. So it's going to go all the way from there to there. That's not very good. We're not utilizing the vast majority of that meter, of that scale. So therefore, resolution, we can say, is far too small for readings. 3.1, this looks like a question to do with moments. First things first, we have a density of 8,030 kilograms per meter cubed. And we have a diameter of 5 centimeters, so let's say 0.05 meters. And we're being asked to show that the weight is approximately 5 newtons. So density is equal to mass divided by volume. If we're looking for weight, then we're looking for mass. So therefore mass is equal to density times volume. So that's equal to density times volume of a sphere is 4/3 pi r cubed. So popping this all in, 8,030 times 4/3 times pi times half the diameter cubed. And that gives us a mass of 0.53 kilograms, but we're looking for weight. Therefore, weight is equal to mg So that's just 0.53 times 9.81. And that gives us a weight of 5.2 newtons. So we're being asked to calculate the moment of the ball. So there's our pivot, then there's our rod going to the ball. That distance there is 12 centimeters. However, we know that we're going to have to add on 2.5 to get to the center of that ball, because that's where the weight is acting from the center of the mass. Therefore, we know the moment is going to be equal to force times distance. So that's going to be our 5.2 newtons that we had earlier. Never use the value that they've given you to check. So they said show that it's about 5 newtons. You never use that 5 newtons unless you didn't know how to get it. You use your calculated value, and then we're going to times that by, well, 14.5 centimeters, isn't it? But that needs to be in meters, so 0.145. And that is 0.75 Newton meters. Next, we've been told that the spring constant of the spring is 100 newtons per meter. We're being asked to find the extension of said spring. So therefore, we need to find the force on the spring, or rather, let's put it in terms of tension in the spring. So here we have our anti-clockwise moment thanks to the ball, but then we have our spring there that's 8 centimeters away, and that's providing a force, a moment that's going in the clockwise direction. We know that from the principle of moments, we know that clockwise moments, or rather sum of clockwise moments, equal to the sum of anti-clockwise moments. I got those the wrong way around. I could therefore say moment due to the ball is equal to the moment due to the spring. So we have this already, 0.75, and that's going to be equal to force times distance, and that force is going to be the tension, isn't it? So just rearranging this here then, so just putting D over there, and I'm going to call that T, so therefore the tension of the spring is going to be equal to the 0.75 divided by 0.08, because it has to be in meters, and that gives us 9.4 newtons. But then finally we're being asked to find the extension. We know from Hooke's law that F is equal to K delta L, or X, whatever you want to call it. We're looking for that, therefore the extension is going to be equal to the force divided by the spring constant. So that's equal to 9.4 divided by a spring constant of 100. So nice and easy. That gives us 0.094 meters. Okay, so what happens when the frame of the seismometer goes down? Frame moves downwards, but ball takes time to do the same. Therefore, line drawn upwards on paper. Ball then accelerates downwards too, and this is due to decreased tension in spring. So it's not pulling the ball up as much. Line returns to 0 or to equilibrium on the paper. Question 4, we have radioisotope stuff. So we're being asked to complete the equation for the decay of plutonium. So we have that and an alpha particle. We know that an alpha particle is always 4 and 2. It's a helium nucleus, then just maths. So just take away 4 from the 238. There we go. Easiest 2 marks ever. 4.2, only 6% is used to generate electricity. So what is the rate that energy is transferred? So let's just have a think about this. 100 watts, you might just want to say, oh, it's just 6 watts then. But let's have a look. It generates 100 watts. Therefore, more going in. So therefore, it's not going to be 100 times 0.06, but rather 100 divided by 0.06. And that gives us 1,700 watts. That's what goes in. Only 6% of that is used to generate electricity. 4.3, constant output voltage of 32 volts. What's the current? Nice and easy. So we know that P is equal to IV. We're looking for current, so I is equal to P divided by V. So that's 100 divided by 32. And that gives us 3.1 amps. Easy peasy. So we're being asked then to find out the max number of components. They each have a resistance of 45 ohms before the output power is reached. Okay, so therefore we have this, and then we have one resistor there, one resistor there, one resistor there, and so on and so forth. You might think that we're going to go down the route of 1 over R total equals N lots of 1 over R. But no, just have a think. We know that whatever current is coming out, and we know what current is coming out, has to be shared across all of these. So let's find the current going through one of these. So V equals IR, so I is V over R. It's going to be 32 volts divided by 45 ohms. And that gives us a current of 0.71 amps going through each one of these. So therefore, our current was 3.1, our total current. Divide that by the current for each one of these components, and that gives us 4.4 components before that maximum current is reached. We can't have a 4.4th component, no such thing. Can we go up to 5? No, we can't, because that would go above the maximum current, so therefore N has to be 4. Only 4 components can be attached. So we have a solar panel. It dishes out 1000 kilowatt hours each year. So we're being asked to find the power output. So we need per second. Kilowatt hours is energy, but we need to turn that into joules, equals 1000 times 1000, because that gets rid of the kilo. And then we times that by an hour, so 3600. So that gives us 3.6 times 10 to the 9 joules made every year. So then we divide that by, well, the number of seconds in a year. So divide that by 365 times 24 times 3600. Yes, there is a shortcut here, but I'm not going to use it. And that gives us 114 joules per second. So that is the same as 114 watts. So intensity of sunlight on Mars is similar to UK. What's the area? Estimate the area of solar panel needed to provide 100 watts on Mars. This is just the dumbest question in the world for 2 reasons. One, the way that it's worded. I don't know why they need to go for the whole Mars and UK thing. Basically, just what's the size of a solar panel? So 114 watts from our previous question is similar to 100 watts, right? So we need a similar size. But then the thing they're asking you to do is basically estimate the area of panel. So we're looking for an order of magnitude. Basically, is it going to be 1 meter squared? So just 1 meter by 1 meter? No, it's going to be bigger than that, isn't it? 10 meters by 10 meters? Yeah, that sounds about right. So actually, we're looking for roughly 100 meters squared. So 10 times 10 meters. Dumb question. I don't care if my students get that one wrong. Okay, multiple choice, just some nice normal stuff, hopefully. So what would result in an isotope of the original element? So therefore, the number of protons stays constant or is unchanged between beginning and end. So we know that alpha results in -2. We know that beta results in +1. So we know that it has to be, well, 1 alpha and 2 betas in some form. So therefore it cannot be A. Is it going to be B, 1 alpha and 2 beta minuses? Yes, it is going to be that, isn't it? Because we have -2 but then +2 because of the 2 beta minuses, and C and D don't make sense either. 6. What shows annihilation? Well, we know that we have to have 2 photons being produced. We saw this in paper 1, so it has to be B. 7. What is not made up of quarks? Kaon is, so it can't be that. Muon is not. It is a fundamental particle, so it's that. Neutron and pions, both made of quarks. 8. What's an antiproton? Well, you should remember Nud and the Pud. But if we're looking for an antiproton, then we should be looking at the opposite. So we should be looking at antipud. So it looks like it's going to be D. 9, interesting question, because they realized that there are 2 right answers. So that one's not in the mark scheme anymore. Let's just have a look at it. It always cracks me up when they have questions with strangeness. They quite often mess these up. Okay, so first things first, we know that there's minus and plus going in charge-wise. So therefore, we have to have a charge of 0 coming out. So therefore, the charge of this has to be 0. So therefore, it cannot be C. Baryon number. Well, we have a baryon going in here with the protons, so therefore it must have a baryon number of 1. so therefore it cannot be A. We know that it has to have strangeness of some kind because a kaon is strange, but here's where they messed up. The kaon could be made with an anti-strange or a strange quark. So actually, whatever this is, it can be +1 or -1. So therefore the answer could have been B or D. All right, we have energy levels for a hydrogen atom. 10, we have a light being produced from E3 to E1. We want ultraviolet, so therefore we need more energy. We need a bigger drop because we need more energy for a UV photon to be produced. The only bigger jump there is E1 to E0, so therefore it has to be D. Okay, we have a proton and de Broglie wavelength. Let's get our equation for de Broglie wavelength. Lambda equals h over mv, or over momentum. The only thing that's changing here is the mass, so therefore we're going to say that wavelength is inversely proportional to m, taking out the constants. This is going up by ×4 because we're going from a proton to a helium nucleus, so therefore the wavelength has to come down by a factor of 4. Therefore it has to be A. Phase difference, 2 points on a progressive wave that are that far apart. First of all, let's find out the wavelength. So V equals F lambda. Therefore, lambda is equal to speed over frequency. So it's 330 divided by 256. And that gives us roughly 1.3 meters. Then we need to find out what is 0.16 meters of 1.3 meters. So therefore we're going to do 0.16 divided by 1.3. And that gives us 0.123. That is roughly an eighth of a wave. If it's an eighth of a wave, then therefore we're looking at a quarter pi, because a full wave is 2 pi. So therefore there's going to be a quarter of pi. First harmonic on a string. Let's get our equation out. F equals 1 over 2L root T over mu. What's changing here? The length and the tension are both doubled. Okay, so that's staying the same. So therefore we can say that F is proportional to 1 over L, and it's also proportional to root T. So actually just let's write that out once more. So root T over the length. So this is doubled. This is doubled too. So therefore that's root 2 over 2. So that's actually going to be 1 over root 2. So therefore the answer is going to be A. Frequency's gone down by a factor of root 2. Okay, diffraction grating. What causes the separation to decrease? In other words, we're talking about theta going down. Let's get our equation. D sine theta equals n lambda. If we're talking about theta going down, then we're talking about sine theta going down as well. So let's check these one by one. A, using light with a longer wavelength, that means that lambda goes up. No, we know that if we use a longer wavelength, we get more diffraction. Check B, increasing the distance between screen and grating. No, that's going to result in wider fringes, isn't it? Because they're spreading out more before they get to the screen. C, increased distance between source and grating. That shouldn't really make a difference, so it's probably going to be D. Let's check it out. We're using a grating with greater slit separation. So if we have D increasing and n lambda staying the same, so that means sine theta must be going down. So yes, that is correct. It's D. White light passes through single narrow slit. What's observed? A, equally spaced. No, because we know that with a single slit we have a maximum that's double the width in the middle. B, central maximum made up of spectrum surrounded by white fringes. No, it's not surrounded by white fringes. It's white in the middle. C, a white central maximum surrounded by coloured fringes. Yes, of course. That's right. D, no. 16, what happens when TIR occurs? Angle of incidence less than the critical angle? No, it has to be greater than the critical angle. Light meets an optically less dense medium. Yes, that is technically true because the N2 needs to be less than N1. I'm really surprised that they've used the term optically less dense, because if they don't like terms like interfere, why would they like that? Whatever, AQA always moving the goalposts. C is the opposite to that, and D is just nonsense. Okay, so we have a refractive index of 1.42. Don't forget the refractive index tells you how much slower light goes in a medium. So therefore, we're going to take 3 times 10 to the 8, divide that by 1.42. And quite honestly, I can already see that that has to be B. It can't be the same, can't be greater, and it's not going to be as low as times 10 to the 7. So it has to be B. Scalar quantity, momentum, no, has velocity in it, that has direction. Weight, no, it's a force, has direction. C, power, yes, that is a scalar, because it's just energy divided by time. It doesn't have a direction. 19, velocity time graph. What's the acceleration time graph? Well, acceleration is fast to begin with, but then it comes down. So therefore, we know that it has to be B, because the gradient of the graph gives you the acceleration. The gradient ends up being 0 in the end. 20, girl jogs at 2 meters per second. Straight line, turns around, returns. What's her average velocity and average speed? Well, her average velocity has to be 0 because, of course, she's going there and coming back. So therefore, it cannot be C, cannot be D. The speed, though, not as easy as it first appears. First of all, we need to find out the distance. So the distance there and back was her speed times her time. So that's 2 times 30. So that means that she went 60 meters. So then, therefore, she went a total distance of 120 meters. Divide that by the 50 seconds that she took, and you end up with 2.4 meters per second. 21, golf ball was hit from the moon. Time of flight was 4 seconds. However, I nearly got caught out with this. Time of flight is there, so we're going to do until the apex there. So therefore, we're going to say the time was 2 seconds to get to the apex. So we can see about this. Let's use S equals VT minus half AT squared. We can forget about VT. So therefore, S is equal to a half times 1.6 times 2 squared. So that's just going to be, well, getting rid of that. So 1.6 times 4 divided by 2. So that's 1.6 times 2. So that's roughly 3. So the answer is going to be A. 22, deep space probe acted on forces right angled to its motion. So we're thinking about circular motion. Hang on a minute. This isn't supposed to be in AS paper, is it? I thought this is just in A level. Whatever. So what's the effect on the forward speed and sideways speed of the probe? So there's our probe, but then the force is sideways, is going that way, and the force is that way. I was briefly acted on. Okay, fair enough. So we know that if it's at right angles, its forward speed is not going to change. So it can't be A, can't be B. Oh, and it can't be D either, so it has to be C. Well, there we go. Forward speed is unchanged. Sideways speed increases. Okay, so a car decreases in mass. Lap time decreases. So what's the explanation? Less friction? No, the more friction, the better. Maximum speed is increased. Technically not, because if the shape of the car hasn't changed, then therefore air resistance is going to stay the same. C, acceleration and deceleration are greater? Yes, because it's got a lower mass, it can accelerate and decelerate greater. The engine's more efficient. No. 24, what is represented by the area under a force displacement graph? Oh, interesting. So we know that force times distance, that gives you the area under the graph, and that gives us work done. So it looks like it should be C. Okay, what is not a unit of power? Oh, hang on a minute. What's this? Joule seconds for B. We know that power is joules per second, so that can't be right. So that must be right. Newton meters per second. Well, let's just check and why not. We know that work done is equal to force times distance, so that's Newton meters. So therefore, Newton meters per second gives you power. So A is correct, therefore it can't be that. C, watts, yes, we know, so, it's not going to be that either. And D, kilogram meter squared seconds to the minus 3. Well, it looks like we're going down the route of F equals ma. We just saw that work done is equal to force times distance, so that's equal to mass times acceleration times distance. So there's kilogram meters per second squared, and then times by meters, and then to make it power, it's S to the minus 1 again. And so indeed that does give us kilograms meters squared seconds to the minus 3. 26, roller coaster is raised to a height of that. What's the maximum possible speed? So this is just mgh equals half mv squared. Conservation of energy, the m's cancel, therefore v is going to be equal to the square root of 2gh. So it's the square root of 2 times, let's just go with 10, times height of 65. So it's the square root of 20 times 65. I don't know what that is with my head, so let's pop that in a calculator. And that gives us 36 meters per second. So the answer is C. 27, we have a mass of 500 kilograms. We have a speed of 10 meters per second, and we have the front 0.3 meters of the car. Okay, so is this going to be a SUVAT question first? I think it might be. So therefore, I mean, ultimately, if we want force, we need mass times acceleration or rate of change in momentum. But if we're using SUVAT, I might as well do this. Okay, so let's do this properly then. So SUVAT, V is 0, U is 10, S is 0.3. We're looking for acceleration, so therefore we're going to use V squared equals U squared plus 2AS. V squared disappears, so therefore we can say that U squared is going to be equal to 2AS. Yes, okay, negatives notwithstanding. Therefore, acceleration is going to be equal to U squared over 2S. So that's 10 squared, so that's 100 divided by 0.6. And that gives us 167 meters per second squared. Therefore, the force is going to be 500 times that. That gives us about 83,000 newtons. So yeah, it's going to be D. 28, we have a current of 20 milliamps. Let's turn that into amps, 0.02 amps. How many electrons pass in 2 minutes? Okay, right. This is one of those times where you can make up your own unit. So 0.02 amps, but that's coulombs per second. But we also know the charge of one electron is 1.6 times 10 to the minus 19 coulombs per electron. We're looking for electrons per second. So therefore, 0.02 divided by 1.6 times 10 to the minus 19. Of course, we want a big number, don't we? So that's why we're doing it that way round, and we need s to the minus 1 on top. So that gives us 1.25 times 10 to the 17 electrons per second. Therefore, times that by 120, that's 2 minutes, and that gives us 1.5 times 10 to the 19. So the answer is going to be B. Okay, combination of resistor and diode. What's this going to look like? You should know that you need to reach a certain PD before current will flow through a diode. So it should be the case here because it's in series with that variable resistor. So we should see that sort of shape. So yeah, it is going to be A. Okay, we have a cell. So what reduces the amount of charge flowing through R in time t? So in other words, current decreases. So if we add an identical cell, if we add another cell, no, it's going to result in the same PD. Resistance hasn't changed, so that doesn't make sense. Put one in series, no, that's going to increase the total voltage. So that's going to increase the current. C, add a second resistor in series. Yes, of course. If we add another resistor in series, we're increasing the resistance. So therefore, the current is going to decrease. 31. Oh gosh, this one looks complicated. So we have 100 megawatts, we have 132 kilovolts, and we're looking for the resistance. Now it's very easy to get confused, this whole thing. Now just remember that that 132 kilovolts is not the PD across the transmission lines. So we cannot use V equals IR or P equals V squared over R with just that 132 kilovolts. So we're going to have to do something else. So let's use our equation P equals V squared over R to find out the total resistance of the national grid. So that's 132,000 divided by 800 times 10 to the 6, so 132,000 squared. And that gives us about 22 ohms. But we're told that 1% of the transmitted power is lost as heat. Therefore, resistance of lines is 1% of whole grid. Therefore, that's going to be 0.2 ohms. Not an easy one, that. Okay, we have a potential divider, blah, 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 which causes the PD across the thermistor to decrease. Okay, first things first, let's get a little drawing there just to make sure that we know what's going on. So we want the PD to increase. So we want the voltage across the thermistor to increase. So increasing the temperature of the thermistor. So if the temp goes up, then that means resistance goes down. So that means that the voltage, the share of the total voltage that the thermistor gets, goes down. So it's not that. B, increasing the variable resistor, that results in its share of the voltage getting bigger, so that means the voltage across the thermistor goes down. Can't be that either. C, reducing the EMF of the battery. No, of course not, that's nonsense, isn't it? So therefore it looks like it's got to be D. Let's just check it. Adding a resistor across the variable resistor, yes. That means that the resistance of this is going to go down, its share of the voltage is going to go down, so that is going to be true. The voltage across the thermistor is going to increase. Okay, we have PD, V across cell with current, blah, blah, blah. Look, we know it's going to be this shape, don't we? Because it's the whole internal resistance thing. Easiest question ever. Finally, 34, we have a battery with a load resistance of 10 ohms attached to it. We have a voltmeter across the battery, so we're reading the terminal PD. So when the switch is off, the voltmeter reads that. So we have an EMF of 1.45 volts. And then we have a terminal PD of 1.26 volts. We're being asked to find out R. So let's get our equation. We know that epsilon is equal to IR plus IR. First thing we need to do is find the current. We can do that from the load resistance. V equals IR, so I is V over R. So that's going to be 1.26 divided by 10, so that's easy. So that gives us 0.126 amps. And so therefore, all we then have to do is rearrange this. We can say that, well, epsilon is equal to the terminal PD plus IR. So therefore, the internal resistance is going to be equal to EMF minus the terminal PD divided by the current. So that's going to be 1.45, take away 1.26, divide that by 0.126. And that gives us a resistance, internal resistance of about 1.5 ohms. And so that means it has to be D. So I hope you found that helpful. If you did, please leave a like. And if you want to see any more papers, then follow the playlist and you'll find more there. See you next time.